Rebecca, just a side note, Rebecca here is currently, she's going into her senior year of electrical engineering at UCSB, and she started her UCSB career participating in our SIMS program, which is for incoming freshmen in science and math, so Summer Institute. So it's kind of fun to have Rebecca here with us on both sides of her degree.
As Wendy mentioned, I'm Rebecca, and this summer I conducted research on the simulation of thermally tunable optical rings, and I worked in Professor John Bauer's lab, and my mentor was Andrew Nethagen, more commonly known as Andy. I don't know about you guys, but for me it's emotionally distressing to kind of even imagine going a day or even an hour without the internet. Like, it makes me sweat. The amount of online data that we generate is a testament to how much we rely on the internet. So just as an example, every minute Facebook users like about 4 million posts, and YouTube users upload 300 hours worth of video content. And in order to process all of this data, we have data centers, which are facilities that contain computers and other necessary hardware that can process, store, and analyze all of this data that we generate online. And the example over here is one of Google's data centers, and it's pretty huge, as you can tell. So another important factor about data centers is data center traffic, so how information is bussed about in these centers. So Cisco recently released a white paper that showed that by 2020, 77% of data center traffic is going to be within data centers. And on the right here, we have an example of a data center architecture. So on the top, we have the core or spine. The second layer is the aggregation or leaf. And then you have the edge or the top of the racks, which were the many racks that we saw in the previous picture. And then that goes to the bunch of servers. These cores, aggregations, and edges, they act as routers or switches that help direct the flow of data in these data centers. And one of the greatest amount of traffic that happens is east to west traffic. So it goes from server to server. And in order to reduce the energy cost of east to west traffic, we need bigger switches. And we need bigger switches because it helps reduce the number of nodes and the number of ports that we have in these data centers. And optical circuit switches fit the job description. So before we go into optical circuit switches, we need to establish what optical rings are. So optical rings are basically made of, in this case, silicon waveguides, and waveguides literally guide waves. So we have two linear waveguides over here, and then a waveguide bent into the shape of a ring, that's optical ring. And when you input light of multiple frequencies into the input port, it goes through and then it passes to the through port. But due to the wave properties of light, some of that light gets coupled into the optical ring. And some of the frequencies of light kind of get killed off by destructive interference. And the ones that survive due to constructive interference. So it's described by this equation. This is optical path length, which is the circumference, times the effective index of refraction. And the wavelengths that do make it have to satisfy this condition. So they have to be an integer multiple of the resonant wavelength. And the survivor wavelengths get coupled into the drop port, and as you can see, this ring is really useful because it acts as a wavelength selective filter. And the cool thing is when you increase the temperature, you actually change your index of refraction, which then changes your resonant condition. So you actually end up shifting your filter to the right. So optical rings are what make up optical circuit switches. So this is a diagram of an optical circuit switch, which has shown great potential to improve cost, scalability, and energy efficiency in current data centers. So this is an N by N optical switch, as you can see, and you can input various wavelengths. And these blocks here are actually subcomponents made up of optical rings and their corresponding heaters. For example, if you just focus on the corner here and imagine that we have a 1x1 optical circuit switch, if you say pass in lambda 1, 2, 3, and 4, due to the properties of the optical ring that we just discussed, it will pass through, let's say, only lambda 2. So you have a reconfigurable switch that can help you switch off on different wavelengths. And my research goals this summer was to create a simulation of these optical rings and heaters to determine the best heater design and configuration that yielded the widest thermal tuning at the lowest power. And how I did that was through photonic simulation software, which was produced by Numerical. So I mainly used two of their solvers, the FDTD and Device. And how I went about it was I imported ring designs and heater designs, which are basically resistors, that my mentor passed to me, and then set up the thermal simulation in Device, and I applied voltage boundaries and thermal boundaries and generated a thermal profile, which was then imported into the FDTD, where the optical simulation was run. And ideally in FDTD, we would be able to see a shift in the transmission characteristics based as an effect of the temperature. So this is just a more detailed visualization. So this is the optical ring, and over here we have the input port where in numerical I'm inputting about 1.5 wavelength to, sorry, microns to 1.6 microns, and then there are monitors at the through and drop port, so I can effectively plot the transmission characteristics. And the square things over here are the heaters or resistors. And by applying 12 volts across the resistor, because it's a resistor, it dissipates heat, and you're able to obtain the thermal simulation. So this is the results that I managed to simulate. So this is the drop port transmission characteristic, and this is with 0 volts, so at room temperature. And then in Device, as you can see here, this is the optical ring and the two heaters being heated up at 12 volts. So you can see that the heaters here don't really dissipate heat very effectively across the whole ring. So after importing temperature profile, you get a really tiny shift. So it looks like you're seeing double, but it's just a shift, like a really tiny shift. So the same goes for the through port. So this is at 0 volts room temperature, and then this is with that thermal temperature profile. And so it looks a little fuzzy, but that's because there's two graphs on there. One of the things that we learned from the simulation was that the heat over here isn't being effectively dissipated across the ring. And because of that, when you heat the ring, you change the refractive index. So there's not much change in the refractive index, therefore there's not much shift in the wavelength selective filter. So for future work would be to design a more effective heater and to refine the simulation framework to be able to test new heater designs, perhaps things with 2 optical rings or other designs, and to also, in the long run, fabricate thermally tunable optical rings, which are the building block of the optical switch circuit. So I would like to give special thanks to Andy and to Aklesh and Takago, who have answered so many of my questions, photonics or not photonics related. And also I'd like to thank Professor John Bowers for giving me the opportunity to work in such a cool lab. And also to Professor Scow, I took a lot of inspiration from your slides. So, and I'd also like to thank Wendy and Jens for all the great support and opportunities and advice. So, any questions?